In this video, we are going to look at the guided notes for section 2.4 in Math 142. So let's get started. Hmm. Here you can see our guided notes for section 2.4. They are on the normal distribution. I'm going to read it. So the normal distribution occurs when you have quantitative data whose frequency histogram approximates a bell shape, like what we see down here. And when it approximates a bell shape, the mean equals the median equals the mode. One property of the normal distribution is that it is symmetric about the mean. Another property has to do with the percentage of data that falls within certain standard deviations of the mean. This property is called the empirical rule. So the empirical rule states, scroll down a little bit, that if you have a bell-shaped curve and normally distributed data, so the mean is in the exact center, meaning 50% of the data will lie above it and 50% will lie below the mean. Then if you go out one standard deviation to the right and to the left, so here, so that bar or this bar, you will encompass 68% of the data. So 68% of the data lies within one standard deviation of the mean. If you go out two standard deviations, so represented by this blue line under the curve, 95% of the data lies within two standard deviations of the mean. If you go all the way out to three standard deviations, kind of represented by the purple line and under the curve, 99.7% of the data lies within three standard deviations of the mean. So we use that empirical rule to answer questions like you see in 2.1. Let's put those on the whiteboard. So here we have example 2.4 from point 1 from your notes. And it's asking us, suppose your class took a test where the mean was 75% and the standard deviation was 5%. If the test scores follow an approximately normal distribution, answer the following questions. So here's how we do it. First, we take the data that tells us that 75%, circle this, was our mean and the standard deviation was 5%. We take these numbers and we put them along the horizontal axis. So our mean here was 75 and the standard deviation was 5. So if we go one standard deviation above the mean, we add that, and 75 plus 5 gives us 80. Two standard deviation above the mean would be at 85 because we'd add 5 again. And three standard deviations above the mean would be at 90 because once again we would add 5. If we go below the mean, we're going to subtract a standard deviation to get to this bar. And so we'll be at 70, 65 for two standard deviations, and three standard deviations would be 60. Now let's see if we can answer these questions. It said, what percentage of the students had scores between 65 and 85? Well, 65 is here, and 85 is here. And we know from our empirical rule that 65 is two standard deviations below and 85 is two standard deviations above. So without doing any further work, we can just look at our empirical rule and say 95% of the students had scores between 65 and 85%. We look at the next question that says, what percentage of students had scores between 65 and 75? 65 and 75. Well, 65 and 75, that's half of what we just looked at. Because a normal curve is symmetric, if from 65 to 85 was 95, then exactly half of that will be between 65 and 75. So 95 divided by 2 is going to give us 47.5%. And that would be our answer here. If we look at C, it asks what percentage of students had scores between 70 and 80. So let's erase this. If we're going between 70 and 80, 70 is here, 80 is here. So that is one standard deviation below and above the mean. So within one standard deviation, we have 68% of the data. This isn't degrees, it should be percent. Now we look at D, which says what percentage of students had a score of 85%. Sometimes the best way to do these types of problems is to find out what percentage is in each little block here. So we're going to go back and we're going to do that because that's going to help us out in the long run. If we look at from 68 or from one standard deviation below to one standard deviation above, that's 68%. But since this data is symmetric, then that means half of that is below and half of it is above, meaning here we'd be at 34%. And here we would also be at 34% because they're going to be the same and they add up to be 68. Similarly, if we go to 95%, that's 2 standard deviations above the mean. That means that from the mean to 2 below and from the mean to 2 above, it's symmetric. So we would take 95 and divide it by 2 and get 47.5%, as we did here. But that is the whole bit. So that covers 1 standard deviation plus 2 standard deviations. So if I wanted to find out what was in this area here, we would need to subtract out the 34. So if we do 47.5 minus the 34% in the middle, we're going to be at 13.5%. So this area here is going to be 13.5%, as is this area here. So that would encompass between 1 and 2 standard deviations, this little block here, below the mean or above. We're going to do a similar calculation between 2 and 3 standard deviations above and below. So let's do that. Let's go with purple, because this is purple. We know that 97% of the data lies almost under the whole curve here, 99.7, excuse me, between 3 standard deviations below and 3 standard deviations above. So if we cut that in half, we'd be looking at what lies here. So if we do 99.7 divided by 2, what will that give us? 49.35? Okay, so 49.35% of the data will lie above the mean to 3 standard deviations, and 47.35% of the data will lie below the 3 standard deviations below the mean. Now, how do we figure out this little piece here? Simple. We subtract out the 47.5 that was these two areas together. So if we take our 49.35 and subtract out 47.5, that's not right. That is not right. What did I do wrong? 47.5, 49. Oh, no. It should be 49.85. I divided this incorrectly. 99.7 divided by 2 is 49.85. So now if we subtract that, we're going to get 2.35. And that's the little bit that is here. And the little bit that is here. Okay, we're almost done. We know that 99.7% lies from from 3 standard deviations below to 3 standard deviations above. Underneath the total curve, we'd have 100%. So if we subtract that, we get 0.3%, very small, that's just 0.3%, very small, is going to lie above and below those 3 standard deviations. So if we divide that by 2, we're going to get 0.15%, which is 0.15%. It's very small. It's 0.15. So why did we bother doing this? So that we could find the percentage of all the students that had scores above 85. We go back here and we look at above 85, that's going to be the 2.35 here and the 0.15 there. So if we add those two together, we get 2.5% of the students would have scored above an 85%. All right. Good job on that. Now let's continue on with our notes. What winds up being important with normalized data is the number of standard deviations above or below the mean. The way to calculate the number of standard deviations from the mean is the z-score. So this is already written in. The z-score is sometimes also called the standardized score, and it tells us how many standard deviations a score lies above or below the mean. Our formula for z-score is that the z-score equals x minus mu, or the mean, divided by the standard deviation. So let's get that down, and then we're going to look at the questions from the example 2.4.1. So here we have our next question, which says, suppose that your class took a test and the mean score once again was 75 and the standard deviation was 5%. If a student earned 87 on the test, what was the student's z-score and what does it mean? So the 87, that's going to be our x in this case. Our mean for this example is 75, so that'll be mu, and our standard deviation is 5, so that'll be sigma. So calculating the z-score would look like this. We'd go z equals 87 minus 75 divided by 5. Now you may want to put parentheses around this in your calculator so your calculator does it correctly, but 87 minus 75 is 12, and 12 divided by 5 gives us 2.4. So 2.4 is that student's standardized score. Now, what does this mean? We would say that a score of 87 is 2.4 standard deviations above the mean because it's positive. Let's look at B. It says this student earned a 73 on the test. What was that student's z-score and what does it mean? So we'll take that 73 and subtract the 75. Once again, you may want to use parentheses for your calculator and divide that by our standard deviation of 5. This gives us a negative 2 over 5, or a negative 0.4. So let's do that this way. So when we talk about what that means, because it's negative, we're going to say a score of 73 is 2.4. Nope, negative is 0.4 standard deviations below the mean. That's what that means. Let's see if we can make that a little bigger. We're going to do a similar calculation on C. Why don't you do it, pause the video, and then we'll check it together. So if you have unpaused the video, you would have done Z equals 54 minus 75 divided by 5, perhaps putting those in parentheses so your calculator does it correctly. And that's going to give us a negative 21 over 5, which is a negative 4.2. So we'd simply reply, because it's negative, that a score of 54 is 4.2 standard deviations below the mean. Bigger. D asks, if a student has a z-score of 1.43, what actual score did she have on the exam or on the test? So here we have to go about this a little bit differently. I'll use black. So we go to our formula for z-score here, and it gives us the z-score. So we put that in, 1.43, and that will be, I've moved it over a little bit, equal to x, which we don't know, minus my mean of 75 divided by 5. When we do calculations like this, what we wind up doing is multiplying both sides by the standard deviation. In doing so, you may remember from an algebra course, that cancels the 5 on the right side of our equation because you're dividing by 5 but multiplying by 5. They undo each other. So you're just left with the x minus 75. That's how we solve it. And then when we multiply 5 times 1.43, we get 7.15. I'm going to do that in black. 7.15. And that will equal now just the x minus 75 because once again those canceled. To solve this once and for all, we add the 75 to our number here, and we're going to get 82.15. So she scored 82.15 on the exam. This one says if a student has a z-score of negative 2.34, what actual score did he get? We follow the same process. So that negative 2.34 will be substituted into our equation for z, and that's going to equal x minus 75 over 5. We follow that same process. We'll multiply both sides by the standard deviation. So we're taking our z-scores times the standard deviation, which cancels the 5 on the right side, leaving us with, I don't know what that is, 11 point something. Pause the video. When we multiply that out, we get a negative 11.7 will equal x minus 75. So to make this work and solve for x, we have to add the 75 to that amount. And that will give us 80. No, we're subtracting actually, because 75 will be subtracting the 11. So we're going to get 63.3 as the test score. Now we'll look at our last one, which says a student has a z-score of 0.5. What actual score? We could really do this on our head, because remember, in our head, z-score, there's the z-score, is 0.5. Remember, z-score is how many standard deviations you are above or below the mean. Since our z-score is positive, we know we're half a standard deviation above the mean. Well, if a standard deviation is 5 units, half of that is 2.5. So if our mean is 75, and we're going half a standard deviation above the mean, we're brilliant and we can impress people with our knowledge by saying that the score that person got on the exam was 77.5. If that doesn't work for you, go back and use the formula and I'm sure you will get it right. All right, let's go on to a couple more items in this section. Here we also will be defining, okay, we just did this problem above. Now we want to define unusual values. Remember in our empirical rule, we said that 95% of the data here with that red line lies within 2 standard deviations of mean. So what that means is only 5%, 2.5 above, 2.5 below, lie outside that. So when we're defining unusual values, we say that an unusual value, we use that 2 standard deviation measure. And we say we call data value unusual if its z-score is below -2 or above 2 standard deviations from the mean. And remember, the z-score gives us that standard deviation. So that's what we call unusual values. The next thing that we look at is the 5-number summary for a normal distribution. Very often when we're given a normal distribution, we're not given a set of data so that we can put them all in order and find the middle and the 25th percentile. That means that in this case, what we have to do is we have to use a formula to find the 5-number summary, which includes the minimum, the Q1 or the 25th percentile, the median, Q3 or the 75th percentile, or the maximum, and the maximum. So that's represented here, and these are the formulas that we use. So to find the minimum, we say that it's 3 standard deviations below the mean. So the calculation is to take mu minus 3 sigma, or the mean minus 3 times the standard deviation. To find the 25th percentile, Q1, we take the mean minus 0.67448 times the standard deviation. That's a calculation that's going to give us the 25th percentile. The mean, or the median in this case, is super simple. It is equivalent to the mean because we're using a normal set of data. Q3 is the mean plus that 0.67448 times the standard deviation. And the maximum is the mean plus 3 standard deviations. So let's get on and try this. So here we have the question for our last example in this section, which says, suppose you and your friends took an exam and the distribution of the scores was approximately normal. The mean was 72 and the standard deviation was 6. Find the 5-number summary. Since we don't have a set of data that we can number out, we have to use these formulas. So our minimum is going to be found by taking the mean minus 3 times the standard deviation. In this case, that's 72 minus 3 times our standard deviation, which is 6, or 72 minus 18, which is 54. That's considered our minimum. To find our first quartile, or the 25th percentile, we take our mean here, and we minus 0.67448 times the standard deviation. So it's going to be 72 minus this number, 0.67448 times 6. Just let your calculator do the heavy lifting here. And what you're going to get is 67.95. Meaning 25% of the data will lie below that because that's our first quartile. Our median is simply just our mean, no calculations required. We just write 72. Q3 is going to be similar to Q1. It'll be 72, but it will be plus the 0.67448 times 6, which if you multiply that out on your calculator, you should get 76.05. And our maximum is merely that 72 plus 3 standard deviations. So 72 plus 3, and our standard deviation we know from up here is 6, which is 72 plus 18, or 90. All right, so that is section 2.4 in a nutshell. I hope this was informative. Thanks for watching.